So one of the primary techniques that we have, that is perhaps the most globally used approach for assessing isometric strength, is using grip dynamometry. The image on the screen shows a standard Takai grip dynamometer, and we're going to talk through this and explain a little bit about how these work and the validity and reliability. So, as I've got written here, there are two methods for assessing grip strength. One frequently used and widely accepted method is the average of 3 consecutive measurements. So we do it 3 times, take the average. In the second, the maximum grip strength value of the 3 measurements are taken into account. Now, Smith, it's going way back actually, it's 1985, reported in a survey that 44% of respondents used the average and 36% used the maximum. Well, let's kind of just unpick that a little bit. It doesn't matter that the reference is old, it's fundamentally telling us something really important, that if you're using the maximum value, there is a real propensity for producing an invalid result. Because particularly when you do this kind of test, there is a potential for the single value to be a function of something the participant has done. They may well have not applied the grip constantly. They may have adjusted their elbow position. They may have adjusted their stabilization position. All of the things which can affect that peak value. If we do an average, and I would argue really 3 is the minimum, I'd be getting into the range of doing 5 of these, the average compensates for that. That's why we do averaging. That's why it's good scientific practice. So here's your kind of first message here is always take the average when we do any form of strength-based testing, irrespective of whether it's isometric, isoinertial, or even isokinetic. So the table here is just to give us some idea of normative values in terms of grip strength. And we've got different population groups. So if we look, for example, we're from the UK. So here we've got data from England. Norm value for males is around about 48.15. Females it's 43.08. This is dominant compared, sorry, male dominant is 48.15 and non-dominant is 43.08. Females dominant 28.3 and non-dominant 25.7. And we'd expect to see a difference between the dominant and the non-dominant hands. And we see this across a range of different population groups, whether it's a 20-year-old or even down to the 45-year-old here, you can see the differences. But this does conjure up something which is very important. And just to reflect on what we mentioned right at the start of this lecture, which is the reference from Sale stated for us very clearly that strength is assessed in newtons or newton meters. And yet grip strength seems to be assessed using a non-SI unit, the kilogram. Well, you would argue, well, does it really matter? Well, it does matter, because fundamentally it's about being effective and proficient scientists. And irrespective, you know, you're working in personal training or the fitness industry, you're still working scientifically. You have to use the right units. And a kilogram is not the unit of force. And that is what you're assessing. You're assessing the force being applied to an object, whether that be a bench press bar or whether that be a squat bar. You're still applying a force. A force is not assessed in kilograms. Now, something that affects our grip dynamometry is the hand. Well, why does it? Here's the grip dynamometer, and what you can see is this is the device itself, and we've got this bar here which the palm of the hand is sitting on this bar, and then the thumb is wrapped around it, and then the fingers are extended over this second bar that's here. And you squeeze this bar, you try and bring this lower bar closer to the handle, and that is in essence the force that's being produced. But you can suddenly start to think, well, hold on, it's gripping. Well, people have different hand sizes. If I've got a different hand size, it may well affect the validity of the test. And it does. We understand that it absolutely does. Now, one of the ways that we can compensate for that is you calibrate the device. You calibrate the device by moving this inner bar, using this ring here, in line with the fold of the fingers to the palm, and so that's kind of where they're sitting. But that's quite rudimentary in terms of the approach that's taken. But we also know that we have different hand geographies. You can see quite distinct different hand sizes here, which affect both the kind of the elongation of the fingers. They also affect the breadth of the hand, the palm, and also the breadth of the fingers. Look at the difference in the hand to the right compared to the hand to the left, just in terms of the breadth of the fingers. You can also see the difference from the wrist to the base of the fingers. Very, very different when you compare these two hands to this hand. So the hand geography absolutely has an impact on the test. It affects not the reliability, because that's a kind of an internal mechanism, isn't it? It's how reliable somebody is, but it affects the validity of the test. How different somebody's hand is, and is that taken into account when we go to different practitioners? So let's have a look at this in terms of the data that we see here. Again, excuse the units that have been used. We've kind of covered that already. So what we've got here is we've got two tables of information, and we've got the mean kilogram force in the top table for the dominant versus the non-dominant hand. So let's just take the dominant hand, and what I want to focus on is just the male scores for the moment. So here you've got male, what is called a long hand, male average hand, male square hand. So if we go back, here's our long hand, you can see, just there. This is our kind of square hand, because you can see you can kind of put a square around this here, and this is our kind of regular shaped hand. But look at the differences in both the dominant and the non-dominant hand in the males, and the same in the females as well, between the different hand geographies. A long hand, because it's got a longer lever, is producing much, much higher forces than the square hand. The square hand actually and the average hand are pretty much the same in the two groups. And we kind of see the same outcomes when we look at the data below, when we compare kind of the dominant hand to the non-dominant hand here. But if you kind of just keep focused on this and look at the same in the females are the same. Take the dominant hand, 28.82, 28.86, 27.26. Non-dominant, 27 to 25 to a low 25. So the geography has an effect in terms of that hand and affects the validity. And unless we take that into account, it's going to change our scores. And it is certainly not taken into account when people refer to normative data. So in other words, the normative data is based upon kind of just thousands of people who've done the grip test. This is what the scores are for the age of those individuals. At no point is the hand geometry being used. And if we look at that in this notion here, what they've done is they've adjusted the grip position. So they've changed the grip position. And what I mean by that is they've changed how much elongation the fingers are going to be allowed to have. So they've started at position 1. They've started with the hand quite tightly squeezed, so the bar is perhaps not in the right position. Position 2, they've aligned the bar up with the lower part of the fingers to the palm. And then 3 and 4, they've moved that bar further beyond the fold and further up the fingers. They're changing, in essence, the outcome. And what you see is kind of a classic length-tension relationship result, because we've moved from kind of a slightly compressed position where we get maybe a little bit too much interaction between the actin and myosin, to an elongated approach where there's very little interaction between the actin and myosin. And you can see the resultant effect on the force that's being produced in both our left and right hand, so in other words, both in the dominant and the non-dominant hand. So it really reinforces that notion of using that basic calibration, but also it tells us that it is so rudimentary, just simply lining it up with a fold of the fingers does not appear to be very scientific. And how can you guarantee that you're producing it that correctly on a test-retest basis? Now, one of the things that's often been recommended to do is to do the test with different shoulder and elbow positions. So different authors use different approaches. Some authors will talk about, for example, having a 0 elbow flexion. So the arm fully outstretched and squeezing with the arm raised. Some talk about 180-degree shoulder flexion, which is in essence the arm is fully extended to our side and doing it. Some talk about a 90-degree shoulder flexion, and so we have the arm out to our side and we do it. And then some talk about, for example, having a shoulder flexion where we've in essence got the elbow at 90 degrees, or we've got the elbow fully extended. And what you can see is because there are so many different varieties of the approach taken, you can see actually that there are ramifications in here if we look at just kind of the total scores. So if you just focus on the total column, elbow flex 90 degrees is 82.2. But you compare that to shoulder flexion 180 is 87.6. It's a 5 kilogram difference between those two approaches. And so what you have to recognize is by changing the mechanics of both the shoulder girdle and the elbow, you're changing the functioning of the flexors and the extensors of the elbow joint. And therefore you're also affecting the ability of the primary muscles within the forearm, which are then affecting the amount of grip that can be produced. All of these are kind of interconnected because it's kind of this kinetic chain that is involved in these movements. So we see the same whether it's males, we see the same for females in terms of you change the elbow and the shoulder position, you change the amount of active force that is being produced. So it means that we have to be much more consistent in the approach that we take. And we have to repeat that process. We can't just, well, we'll just take a grip score. It doesn't really matter what we're doing. We'll just take a grip score and not control for anything. This really shows you how fundamentally important it is to control both elbow and shoulder flexion. And it's the same for all measurements, but this is a really good kind of education in this in relation to this case, grip strength. And we mentioned a moment ago about normative data. So you've got normative data set here for males and females. This shows you your distribution plot. So here you've got kind of the frequency. So the frequency plot here, the kind of the score that you've got for this kind of largest proportion of the population here is around about, what's that, about 55 kilos in the female, and then in the male scores here slightly different in terms of what's going on, but we're around about 50% of the population is here, and we're producing a score in this example here. It's getting close to, what is that? Getting close actually to about 105 kilograms, quite high actually. If we take 50% of the population for the females, actually it's relatively similar actually in terms of here's the 50%, but look at the value, it's significantly lower. This is kind of, this is actually an extreme of our population group. We mentioned this earlier on. There was that kind of data, wasn't there, earlier on that suggested, well, there was a correlation between the medicine ball throw and in that case it was correlated against isometric strength. Well, it gets quite interesting because what we know is isometric force is absolutely correlated. You can see it here. We have to be cautious with correlations. Remember that correlations are the lowest form of statistical analysis and fundamentally do not show causality. They just simply show association. But that notwithstanding, there is this association between the two, and we see this with grip strength. That incredibly, grip strength is highly correlated to the notion of 1 rep max. It's correlated to isoinertial strength. So people who do well on the grip will do well on an isoinertial strength test. In other words, it lends weight to the idea of grip being used as a proxy indicator of whole body strength.